Now here, we're cloning the weights from Conv, and then we're changing or reshaping the tensor. So let me show you what this looks like. The weights of the convolutional layer are these. So we're going to clone them, but then also we're going to change the shape to this. So let me run this, and then I'll explain it. So conv, that weight has this shape, 64 by 3 by 6 by 6. But then before we save the w underscore conv, we want to reshape it to 64, 108. So here we're inputting the dimension. This is 64, the output channels. And then this -1 combines 3 times 6 times 6 into a single dimension of these same values. So the 4-dimensional tensor becomes 2-dimensional. We can also see it here. So conv that weight is 64 by 3 by 6 by 6. And the moment that I run this, wconv will be 64 by 108. So this new variable, wconv, has been created, which essentially has the same values as conv, but reshaped, as you can see here, 64 by 108. Now here, let's start unpacking one line at a time, and I'm going to focus mostly on the collab right now. So this is the line that we want to calculate. I have commented it because I want to analyze it first. So now we're going to start applying the fuse conv formulation. So I found this website from Nina and Marcus, where he explains the steps and the math for fusing a batch normalization layer and a convolutional layer. So important to note that during runtime, during prediction, the functionality of batch norm is turned off. And this is done to save computational resources and simplify the architecture. Given that we don't need to calculate the mean and the variance of our input images, we only do that during training. So it is better to merge both layers so that we can be computationally more efficient. So our convolutional layer is essentially this right here. The weights of the convolution are input image and the bias term. In our case, the bias term is 0, set to none. So wx plus b, that is the convolution. And then the output is the input to the next layer, which is the batch norm. So wxb, where the input is the convolution. So we can calculate the new weights by matrix multiplying the weights of the batch norm and the weights of the convolution. And then we can calculate the new bias terms by, again, dot product or matrix multiplication of the weights of the batch norm and the weights of the bias term of the convolution, which is 0 in our case, plus the bias term, also shown here. So with these two operations, we calculate the new weights right here, and we calculate the new bias term right here, multiplying these and then adding the batch norm bias term. In our case, this is 0 because this is 0. So our new weights will be these, and our new bias will be this. Now, you can also see how batch norm works going to the actual research paper. But this is mostly focused on the batch norm during training. We're going to focus on here so that we can actually do the fuse batch norm and convolution. So this representation and this representation are equivalent. There is, of course, much more level of detail here, which is why we're going to focus on this formula. So we have on the numerator the weights of the batch norm layer, and in the denominator we have the variance plus a very small term for stability. The first thing that we're going to do is print these terms here so we have a better idea of what those are. I also like as a best practice to print the shape of the tensors, especially if we're doing matrix multiplication or calculating that product, so that we have a better idea of the output shape of the tensor. So epsilon is a small value. Added for stability, it prevents us from dividing by 0. And then the variance of the batch norm of this first layer is 64 because we have 64 output channels and the batch norm is calculated for every channel. And these are actually the values of the batch norm variance. The shape of the batch norm weights are 64. Essentially, we have a vector with 64 values. And these are the corresponding values here. So the first thing that we're going to do is divide the batch norm weights by the square root of the sum of epsilon and the running variance. And we're going to store it in this variable here just to be able to display it. So essentially, we've performed this operation right here, which is also equivalent to this right here. Now, we have calculated these 64 values, but as you can see here, in order to be able to perform matrix multiplication between these two matrices, we need to create a diagonal matrix with these values within the diagonal. And this is essentially what the torch diagonal function does, which calculates or generates a diagonal matrix of those values. So let me print this. And before, we had a shape of 64, and now we've created a tensor of 64 by 64, where the values of the batch norm weights are in the diagonal. So if we go back to our case in VS Code, let's run this. WBN is the 64 by 64 matrix with the values 42.59, 42.59. And then here, we're going to perform the matrix multiplication, and we're also going to change the shape. But let's do it in our Colab environment. Let me run this first. So our batch norm weights have a shape of 64 by 64. The convolutional weights 64 by 108, as we calculated earlier. And then the matrix multiplication of 64 by 64 by 64 and 108 will be 64 by 108. You can also see it here, where the dot product or matrix multiplication of two matrices, n by m, with another matrix of m by p dimensions, the result is an m by p tensor or matrix, as we have in our case. So it will be 64 by 108, shown here. And now we are changing the shape of that tensor. So given that fused conv.weight has a shape of 64 by 3 by 6 by 6, our 64 by 108 tensor will be reshaped to this shape. And then here, perform the matrix multiplication of the weights of the batch norm and the weights of the convolutional layer. This operation right here will change the shape to 64 by 3 by 6 by 6. And then we will override the values inside fuse conv.weight with these new values. And that's what the copy underscore function is actually doing. That copies the elements and returns self, overriding the previous values that we had. And then here, to be able to see it better, I'm printing the first index. That's why we have here 3 by 6 by 6, 3 by 6, 1, 2, 3, 4, 5, 6, by 6, 1, 2, 3, 4, 5, 6. And here, I'm saving it to this variable before we update those values with the copy function, so that you can see that the values that we had are different from the current ones since we've performed this operation right here. And we obtain 5.56 to the power of -2. So let's make sure that we get the same results from VS Code here. So fuse conv, you can see that the first value, 5.56 times 10 to the power of -2.